In this module, let's look at clocks. In this module, let's identify what is a clock, how a clock is defined, what is the clock period, pulse width, duty cycle, and all the different properties of a clock. And we'll also look at how clock actually is propagated in a design. In digital circuits, clocks play a vital role because they trigger the storage of these memory devices, and also they control your state machines. So if you have flops or latches in your design, you're using a clock to trigger that storage into those flops and latches. So if you think of the Verilog language, anytime you see an always at pause edge clock or always at neg edge clock or always at clock, these are the storage devices that you're creating through Verilog. And when you see the pause edge clock, that triggers a creation of a positive edge flop. And neg edge clock triggers the creation of negative edge triggered flops, and latches are created via the always at clock constructs. So each clock actually determines the period of the clock, determines what is the goal of that particular path. So if a particular clock is actually triggering the storage, then basically one clock period is what is required in order to meet the timing for that particular path. So basically these clocks are these periodic signals that are broadcast, and therefore they are generated either on the chip or outside of a chip. And when generated outside of a chip, it's via crystal oscillator, or if you generate it within the chip, you use phase lock loop or PLLs. When you associate those ideal clocks with an actual port, now if the port actually has a rising edge for the initial edge, then basically that clock is considered as a positive clock. And then a negative clock would be if the leading edge is actually a falling edge. When you associate those ideal clocks with an actual port, now if the port actually has a rising edge for the initial edge, then basically that clock is considered as a positive clock. And then a negative clock would be if the leading edge is actually a falling edge. The clock has multiple properties, one of them being the clock period, which defines at what interval the waveform repeats itself. And then you have the rising edges and the falling edges, and the rising edge is when the clock is going from low to high, and for when the clock is actually going from high to low, then that edge is called the falling edge. And the pulse width is basically determined as when the clock is high compared to the low. So the pulse width is how much is the clock high. In some designs, it is important to understand what duty cycle is because there is a mixture of positive and negative edge triggered flops, and or there are latches in the design. So when there are transfer of data from different level flops, whether it's positive edge triggered or negative edge triggered or latches, there is actually the reliance on a duty cycle. How often does the clock stay high? So that is actually important because for in the case of latch, when is the latch transparent or when is the latch opaque is actually determined by the duty cycle. It's also important what kind of flop is receiving the data. So a duty cycle actually can determine when is the transfer of data actually happening. So in certain cases, duty cycle actually helps you, but in most designs where it's actually either just positive edge triggered flops or just negative edge triggered flops or just latches, the duty cycle doesn't play much role. So in this example that we have here, if a clock is defined by its period of 4 and then the edges of 0 and 2, then what happens is the duty cycle is calculated as pulse width high divided by the clock period, which is in the waveform that is shown, which is 2 minus 0 divided by 4, and so we have a 50% duty cycle. On the bottom one, the pulse width is high only for 1 unit, and so therefore it's a 25% duty cycle. Try this activity to improve your understanding. In any design, a clock triggers several flops and latches. So these clocks are considered high fan-out nets, and they need to reach or traverse the entire design to reach these flops and latches, and the in order to actually keep the integrity of the clock signal, it needs to be constantly buffered. And these buffers can be in different structures. And the most common forms are known as clock trees or clock meshes. And so you would actually see different types of buffers along the clock tree and or clock mesh, and generally they're referred to as clock trees. And so you might actually start out with a drive booster and a bunch of repeaters, and then different kinds of buffer strengths placed along the length of the tree while it traverses to reach the flops or latches. So in the case where your design does not have any clocks, and typically during synthesis the clock tree doesn't exist, and so therefore you need to mock the effect of a clock tree into your design. And this stage during synthesis, it's known as the ideal mode. And then when the clock buffers are inserted into the design, it is known as the propagated mode, where the modeling that we have done is actually replaced with the actual clock information, and thus it's called the propagated mode. As we've seen before, transition time is the time taken by a signal to change states. So in the case of a clock, this is known as the clock slew, and clock slew is actually essential in ideal mode. So we need to define the clock slew in ideal mode because ideal clocks typically don't have any rise times and fall times. It's instantaneous. Whereas once the clocks are inserted, then the SDA tools will actually calculate the slews of the clocks through the buffers that are actually inserted. Because we're talking about real clocks, and these clocks are generated by these clock oscillators or PLLs, there is a certain uncertainty where the period and the duty cycle can vary slightly because of the circuitry that is generating these clocks. And this is considered as clock jitter, and each clock oscillator actually comes with the datasheet actually comes with definitions and also the values for all of these different things. And so therefore the clock jitter is actually provided. And also sometimes there is variance between when a clock arrives at different points in the design because of the buffers and everything that is actually inserted. And so ideally these clock trees try to be adjusted so that there is not much variance in when clock arrives at the different points, but it's inevitable because it is a real design. And so therefore you actually use a particular value of uncertainty called clock uncertainty, which is actually calculated for all the different clocks in your design, and you use that value in your calculations when you're measuring your timing. So basically, clock uncertainty thus becomes your whatever clock variation is due to clock jitter, plus the worst case clock skew for the setup, and for the uncertainty for hold is actually your best clock skew, and that is what is actually used to determine the uncertainty. So basically, it's a way to add pessimism to your design. Okay, and when you use uncertainty, you're implying that you're either tightening the constraints or the clock a little bit more than what normally your design actually would be. And so therefore, especially in the case where your paths start from one domain to another, then you basically need to make sure that all of these are defined. We need to model when the clock arrives at different points in your design, the flops and latches and so on. And when you try to model what time that particular clock is arriving at any given flop, that would actually give you the actual time that is required for that particular signal at a particular flop to reach the next flop and so on. So this kind of modeling is actually done via the latencies, and you need to define two types of latencies. One is the source latency and the other one is the network latency. The source latency is what the clock itself sees before it even comes into the design, and so that is defined as the source latency, and the network latency is the one that is modeled via your clocks, the clock buffers and things like that. So any buffering that you actually do inside of your design, that is known as the network latency. So these latencies are basically modeling your effect of the clock before and after it comes into the design, and what happens to it through the buffers and so on and so forth. So your total latency obviously is the combination of your source latency plus the network latency, and they're also referred to as insertion delays. And so at any given flop or latch, your latency is actually the combination of these clock latencies, whether it's source or network latencies. So obviously, the ideal clock is modeling the effect of when the actual clock buffers are placed. Take a minute to do this activity to improve your understanding. Your signal data is actually captured and stored in these flops, and basically when you need to move from one flop to another, the signal is considered launched from one flop and captured on another flop. And so therefore the launching clock is the clock signal that triggers the data to actually data or signal to go through the combinational delay, and then it is captured at the capture flop. And the clock that actually launches the data is called the launch clock, and the edge of the clock that actually launches that particular data is called the launch edge. And for the capture side, the capture clock is the one that captures the data, and the edge that captures that particular data is called the capture edge. And there are certain requirements before a particular data signal is safely stored in the particular flop. So you need to actually determine whether that data has arrived at the right time, and if it has satisfied certain requirements, and we will call them setup and hold requirements, and we will talk about these later on. But we need to meet those requirements before that particular data is safely stored in the device. And so therefore, we will look at that later. But as of right now, the launch and capture edges are essential to be understood. In this design, there is only one clock, and that single clock is actually launching the data on one edge, and that launch clock is the same as the capture clock, but the launch edge is actually different from the capture edge. So it takes one clock period for the data, in this case, to be launched and captured at another edge by the same clock on a different flop. So that particular one clock period is basically what is the requirement for the design to successfully meet the timing on this particular path. So we will look at more examples of what the paths look like, and also what the launch edges and capture edges look like for different flops and clocks in your design. When you have multiple clocks in the design and you have data transferring from one clock to another, the worst case launch and capture edges, they're not necessarily intuitive. So you need to follow certain steps to figure out what is the worst case data transfer. And so in order to do that, first you need to determine what is the least common multiple or least common denominator of these periods. And so in the example that is shown, between clock period 4 and 6, the LCD or LCM is 12. And when we have the edges aligned, both of the leading edges of both the clocks are aligned, then you unroll the clock so that, again, the leading edges of both the clocks meet. That's called unrolling. So you need to figure out how much you can unroll, and typically the LCM would be where the leading edges align again. So as you can see in yellow, the leading edges again align at 12 and at 0. So in order to determine the worst case launch and worst case capture, you need to actually do this so you can see all the different edges that would repeat themselves over and over again. So now you can determine all the different transactions that happen between the two clocks and determine the worst case. Let's look at an example with multiple clocks. And if you have clock periods of 4 and 3, and the LCM is 12, and so we would unroll the clocks up to 12 nanoseconds in this case. And so for a clock 2 to clock 1 falling to rising transfer, what you're trying to look for is what is the launch edge and what is the capture edge. That is the worst case scenario. So we are asking for a falling to rising. So we look for the worst case falling for the different edges, and then look for what is the most restrictive capture. So we try different edges, and we try to capture what is the worst case scenario. And so in this case, the worst case scenario is actually the launch edge at 2 and capture edge at 3, making that the worst case scenario. But there could be other ones. I mean, you keep looking to see what is the worst case edge. But because we are looking for a falling to rising, that particular example actually is one example. You can try to look for the same thing at 6 and 9 would be the rising capture. So there are only certain number of falling edges for clock 2. So there is one at 2, there is one at 6, and there is one at 10. So, and the corresponding capture edges would be for at 2, it's 3. For at 6, it's actually at 9. And for the 10, it's at 12. So obviously the worst case capture is actually shown in the graphic right there, the launch edges and the capture edges. Try this activity to improve your understanding.